alkanes, alkenes very briefly because we did look at them last lesson, and just get ideas of how to get all these reactions in your head. Hopefully a number of them will be familiar from level 2, but some of you haven't done level 2 organic, so you've got a lot of reactions to learn. So we'll think of different ways we can try and get all this learning work in your head. Okay, so we'll go over alkanes and alkenes very briefly, and then it's the haloalkanes, alcohols, amines, aldehydes, and ketones. Next week, hopefully we'll finish this all this week, and then next week we'll do the carboxylic acid derivatives and proteins and so on. So just as a reminder, Markovnikov's rule and Zaitsev's rule. You need to know these rules for addition reactions for Markovnikov. I've sort of underlined the A for A for addition and M for Markovnikov because they come up, you know, A is before E for elimination and Markovnikov M is before Z. Or if you spell it the other way, Zaitsev, it's before S anyway. So perhaps that's one way you can link. Markovnikov is to do with addition and Zaitsev is to do with elimination. And the sort of way to remember it is the rich get richer. Please don't use that in the exam, okay? You're not going to get anything for it. You have to explain. So basically what you're saying with Markovnikov, the hydrogen adds to the carbon of the double bond that has the most number of hydrogen atoms. So here's my double bond. The red one only has one hydrogen, the yellow one has two, so the hydrogen is going to add to the yellow carbon. And so this will be in the major product, and I'll get some minor product because some of the hydrogen will go and add to the other side. Okay, so you sometimes get asked, oh, you know, the major product of this reaction is blah, 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 and they expect you then to draw the right product. The elimination is where you look now for the leaving group. So it's elimination, it's normally for the haloalkanes or the alcohols. You don't really get it with the amines. You don't have to learn any eliminations for that. So it's just the alcohols and haloalkanes. You look for that carbon that the functional group is attached to, and you go, right, I've got this carbon, the blue one, and I've got the yellow one. So which one has got the least number of hydrogens? Because for elimination, it's the poor get poorer. So which one of these has the least number, the blue or the yellow? So Caleb is typing the blue, correct. So the hydrogen is going to leave from the blue one because they've got the least, so they're going to lose even more. Okay, so the major product will be with a double bond forming between the red carbon. It has to be the red because that's where the functional group is. Remember when I was speaking about where is the reactive center? It's always the carbon of the functional group. So the red carbon is going to be involved, but the major product is where the double bond forms between the red and the blue, and the minor is where it forms between the red and the yellow. So do you think you've got those two rules clear in your head? It will come up in reaction schemes and various things like that, but mainly reaction schemes. And then this is something, I'm not going to really go over it again, but this is the, just to show, alkanes pretty much burn. That's what they do. They don't really have a reactive center, so you don't really have nucleophiles being able to come in. There is also a reaction that you learned last year under where it reacts with chlorine under UV light, but that's actually quite a horrible reaction. You get so many multiple products, so it doesn't really come up in level 3 as such. Okay, so that was the alkanes. Alkenes, you've got what are called the 4 H's. Okay, and that is the hydrogenation, halogenation, hydrohalogenation, and hydration. Okay, so if I'm adding to the double bond HBr, what do you think this reaction is? Hydrohalogenation, halogenation, hydration, or hydrogenation. Hydrohalogenation. You're adding a hydrogen, so that's the hydro part, and the halogen. So, okay. So I'll just go very briefly. That's hydrogenation. This is also actually a reduction reaction. Remember, so reduction is like adding hydrogen or removing oxygen. I mean, you know it's reduction because you can see that hydrogen gas is being oxidized. It's going from an oxidation number of 0 to +1 over here. But the main type of reaction is considered addition. We're adding across this double bond. But if you said it's a reduction, it shouldn't be marked wrong. Halogenation is also a straightforward addition. It's not a reduction or an oxidation. Oh, sorry, that one is as well, because it's going from 0 to, in this case, it'll be -1 over there. Then hydration is, this is a straightforward addition, okay, not an oxidation or reduction. This one is also an addition, but we're using, oh, okay, we've gone down there, but this one up here is a permanganate, and we know that permanganate is a strong oxidizing agent, and you become a diol over here, 2 OHs added. And the last one is the hydrohalogenation. Now the two tests are, I'll see if you saw last time, which is the debromination, the decolorization of bromine, or, and I'm going to move this one along, is the color change, where, okay, just put that in there. Alkane doesn't change color, alkene it does. So I'm just going to move it on. You can see the color is just disappearing, and if I move it on here, he's shaken it, and you can see the color has changed. So you do need to know those changes. And this we looked at last time is basically we're adding 2 BRs. Here, whenever there's 2 H's, there's no difference between them, so Markovnikov doesn't apply. Here we're adding an H and an OH. So does Markovnikov apply, or doesn't it? Yes, it does. So whenever you're adding H with something else that's different, think Markovnikov. Here it's 2 BRs, 2 H's. You don't worry about it because it's the same thing. And then hydrohalogenation, again, Markovnikov applies because you're adding H with something else, a Cl. Okay, so this, I'm just going to pause very briefly, have a look. Can you match up the type with the reagent? So you don't have to type anything, I'm just giving you a little bit of time just to try and get this in your head. So very briefly then, okay, hydration, I hope you matched it with hydration, water. So look for something with water, okay? But if you just wrote water in your reaction conditions, it would be marked incorrect. You do need the conch sulfuric acid with it, okay? Then halogenation, it could be Cl2 or Br2, one of the others, great. Okay, hydrohalogenation, it's a hydrogen with a halogen. So you could have used HBr as well. Both of these is hydrohalogenation. Okay, then hydrogenation, the platinum is the catalyst. Remember what I said, reactions, organic reactions are slow, so they need heating, and they often need catalysts. So actually this really acts as a catalyst here. That is acting as a catalyst as well. So that's why we have those things. And then, of course, the test where the brown color fades is the bromine, and where the purple color fades is the permanganate. So one way you can try and learn this is to start building up a table of the different types of reactions. So addition reactions. What addition reactions have you come across so far? Elimination reactions, oxidation reactions, and then just starting to list them and building up like across a matrix, and it might help you put the things together more easily. Another way is, and I think there are these cards up on Ottle, is to play what I call, I don't know if you've ever played rummy. Has anybody played rummy? No. Okay, sort of. I know one student last year said, oh, my granny plays it, so that puts me in my place. So it's a type of card game. And there's different styles that you can play it with. But basically, you've got to put sets of 3 together. So in the person that wins is the one that gets rid of all their cards. So the sets of 3 is, or 4, yep, is where you've got your reactant, your reaction conditions, and your product, is the way I've adapted it for this. Okay, and then you have to pick up a card and discard a card in each turn, and I always play a version where you can add on. Yes, Rummy Cub is a fun card game, but I don't think this matches Rummy Cub very, very well. So I make it that if somebody else has already put a set down, you can use those around, and you have to discard a card, and the one who gets rid of all their cards wins. Yep. Okay, so here we've got player A and player B. Just to, if you were going to play this at home, is you pick up 7 cards. Now I'm showing what cards they've got for the purpose of this game, but of course player B can't see player A's card and player A can't see player B's card. So there's a deck that you pick up the cards from. There's your discard pile that you're going to throw it down on. So if player A picks up that card, he looks and he goes, okay, that's a reaction condition, so is that, so is that, so is that, so is that. But can I use any of these as a product and as a starting material? And yes, you can. If I add spheric acid and water to an alkene, I'm going to get that alcohol. And I know that that's going to be the major product. So I can put 4 cards down and, well, player A, and he can discard a card. And he's decided to, because they all reagents, discarded one of them. Now it's player B's turn. So player B picks up a card, nothing there to react, so he's thrown it away. Okay, because none of these are both haloalkanes, and he's got no alkenes here to do anything. This game I've set up is just with alkene reactions, so it's quite limited. You have to have an alkene as a starting material. So it's player A again. Player A picks up a card, nothing there, throws it away. Player B's turn, picks up a card. It's still, as you can see, not an alkene, so he's got to throw it away. Player A, and so we carry on. He's now finally got an alkene, but he's got nothing there to help. And so it's player A. He's picked up a card, nothing. Now it's player B. He's picked up something. He's now got something, okay? Because he can make that hydrogenation one. And he throws away a card, player A, and it's going to finish just now because he can get rid of all his cards and discard. So that one's one. If this one now carried on, because you could say player A started, so give player B one more turn if you really wanted to. If player B picks up a card, as I say, normally you don't see what cards you're picking up, by the way. I've just had to make it all facing. So if player B picks up the card, then he actually can do something. Because he can say, okay, my alkene can either react that way, or I can make it react this way to form the alcohol. This is good for building up reaction schemes as well, which is important to know. And I can also say, and that's a minor product, I can also say, right, my alkene, and I'm joining up this group with that, can react with the bromine to form my dibromoalkane, and I can throw away my alkane. So, chloroalkane. So you can say that they're both one, it's up to you. But it would be good, and you can just build up your cards and add in more reactions, and particularly you can start building up reaction schemes. So you start seeing the reactants as being able to apply to different reactions. So anyway, that's one way. And if anybody can put that into a computer program, that'll be wonderful, and then everybody can have fun with a computer game. Okay, so that's alkanes, alkenes, some ideas of how to learn it. Now, haloalkanes. Now, going back to those tips is, remember, work out what the reactive site is, because that's going to be the area that's going to change. And then think of what's going to happen. Am I getting a nucleophile coming in, or what is happening? So with my haloalkane, chlorine is more electronegative. So this is slightly negative, my carbon is slightly positive. So is it going to attract nucleophiles or electrophiles? Nucleophiles, good. So it's going to be something, a nucleophile is something that's rich in electrons itself. So if I have OH minus, do you think that's a good nucleophile? Yep, because it's got a negative charge. Okay, so it's not one of these absolutely fantastic, I'm going to kill everybody my way to get this sort of thing, but it is negative, so it'll be attracted to something that's positive. So if I now expand my haloalkane, there's my negative and there's my slightly positive area, my negative is going to approach and form a bond, okay, and my bromine is going to get kicked out, or my chlorine, sorry, is going to get kicked out as a chloride. So I'm trying to show that the electrons are going with it. Okay, so my leaving group is bromide, so there's my OH, and my bromine is gone. There are my two hydrogens, Okay, now notice that this is aqueous. This is happening in water. So my OH is, I'm getting a lot of OH also coming sort of from the water as such, as well as what I've added. Because if it's a basic solution, the H2O can also, swap the H2O can be an OH and so on. Now, if I have an alcoholic, no, it wouldn't react with plain water because water is not a strong enough nucleophile. But if I add lots of base to the water, as I say, water can interchange and become, this water molecule can become OH, and that OH now becomes water, and so on. Distilled water also wouldn't react. It's just not a strong enough nucleophile. Okay. Now we've got an alcoholic, and I'm heating it up as well. That triangle means heat. So if I push for more extreme conditions, okay, so alcoholic or more concentrated, okay, then what happens? My my OH can grab the hydrogen from here. Remember I said over here the aqueous system, the OH can grab a hydrogen from water and form another OH, and that becomes water. But here, if I make it much stronger conditions and give it more heat, so it's more energy in the system, it can take this hydrogen, because remember this bond is actually quite a strong bond, but it can actually remove it, so those electrons now will form a double bond, and the chloride goes off. Okay, or in this case bromide. Sorry, I just see I've got this chloride and I've made it bromide. Doesn't matter, it's a halogen. And so we get the double bond. Okay, it has to be alcoholic because the ROH bond doesn't break as readily as the HOH bond. So HOH, an aqueous, that, you'd get the substitution happening, but you won't get that sort of thing happening in ROH, so that's alcoholic. And so, especially with a bit of heat, you're going to get the elimination. And so products would be H2O and chloride, or if this was chloride, it would be, because you can see it's OH and then plus that hydrogen as well. Okay. So April, it can only break the H bond of the middle C. Yeah, it's got to. This, as I say, is the carbon that is slightly positive. So if this was on the end as it is now, there's only one other carbon where the hydrogen could be removed from to form a double bond. If, however, it was in the middle, say I had another methyl group over here, then it could take from this side or from that side. And then, yes, then you'd start applying Zaitsev's rule, okay, where the one that's got the least number of hydrogens loses the hydrogen. So, April, have I answered your question? Okay. Yeah. Right. And then, as I say, it's the reaction conditions. Always be aware, because sometimes people just focus on the nucleophile and they just go hydroxide, and that's not good enough for the exam. You've got to say it's an aqueous or it's an alcoholic, and I mean, this has most probably got some heat too, but this really does mean it needs a stronger heat as well. Okay, so here's an example. We're not going to watch this whole thing, but can you see he's now pouring in a substance, 2-chloro-2-methyl-propane, and it's the substance over here. So, and it's a liquid. So when you're watching these reactions, ask yourself questions like, why is it a liquid? Why is that a gas? Okay, and so on. So I'm going to move a little bit further. Notice he's heating. There was one of those, I think the very first tip of organic reactions are slow and it needs heating. He is reacting it also with KOH and ethanol. If you listen to it, I think it does explain things. So remember the previous slide we had with elimination. It's a hydroxide, alcoholic hydroxide with heat. So you can see he's heating. And can you see there's a gas being formed? Now, why is it a gas? Why aren't we forming a liquid? Why are we forming a gas? There's a high temperature, but my haloalkane isn't becoming gaseous. Right, I think you're on the right track there, Joe. We're forming an alkene. Now, an alkene, it's lost the chlorine, so it's much lighter now. So those intermolecular forces of attraction are much weaker, so it's going to be gaseous. It's now pretty much nonpolar with not much mass, so those intermolecular forces have weakened. And if I just move it on a little bit, hang on a minute, I just want, okay, he's testing there with bromine. And can you see it? It is going colorless. Okay, it's pretty much colorless. It's not very clear. Okay, it's definitely colorless. So that is a test to show that you had an alkene because it decolorized the bromine. And then this other test is actually alkenes, hydrocarbons, they burn. And actually you can see the difference between the alkane, alkene, and an alkyne of similar masses with an amount of soot they give off when they burn. So the more yellow and sooty the flame, the more likely it's going to be a double or a triple bond. But that's not important at level 3. Okay, so when you watch these videos, ask yourself questions all the time. Why are they doing that? Why are they doing that? Because if you were in a lab, you would be doing it and the teacher would be explaining as well. Okay, so just like we had 4 reactions for the alkenes plus some tests, we've got 4 reactions for the haloalkanes. So 2 of them are actually fairly similar. We're forming amines. One is primary amines and one is secondary amines. So concentrated ammonia, and we do it in alcoholic. We don't use aqueous because we don't want to form the alcohol. We just want to form the amine, because OH minus is actually a stronger nucleophile than NH3, and that's why we have it alcoholic. If we react it with an amine, you can get a secondary amine. Now, you do not have to know how to name these for the exams or for the spectroscopy standard. So you're welcome to want to explore it, but you don't have to know that. Okay. So in the exam, sometimes I'll give a name of a secondary amine, and so I've included it so you aren't thrown by, like you're wondering, where does this N suddenly come from? Okay, it's just one of the ways you name secondary amines. Okay, otherwise, aqueous, we've already seen, you form the butanol, or the alcoholic, we've seen, remembering your site Ceph with your major and minor product, you're forming your alkene. Okay, right, so if I If I want to make primary amines, do I choose 1, 2, or 4? Choose 1, correct. If I wanted to make a secondary amine, 2 or 4? 4. So why should water be avoided to make amines? That's alcoholic, and as I said, it's okay, because you'll see April, you're on April 4. The OH is a stronger nucleophile, so we don't want water around, because if we add ammonia to water, we're going to form NH4OH, so we're not going to be adding the NH4 plus, because that's got no lone pairs now to react, and you're just going to form an alcohol instead. Okay, so that's what I'm trying to show here. That's not going to be a nucleophile anymore. And the same thing with an amine, it's also got to be alcoholic, because if I have water around, I'm going to form it's accepted a proton from the water, and that won't be a nucleophile either. When you do the 3.6 standard, then you start doing this in a lot more detail as well. So the standards do cover similar things, like you've seen intermolecular forces come up in organic chemistry quite a bit. It's not directly examined, but knowing the 3.4 stuff helps your 3.5, and you'll find the same thing with 3.6. Okay, alcohols. Alcohols are similar to the haloalkanes. The difference is I actually have got 2 reactive centers. I've got my carbon that's slightly positive, so that is going to attract nucleophiles, just like the haloalkanes. But I've also got my negative O. Now, chlorines and fluorines and bromines don't like sharing their lone pairs, so they won't act as nucleophiles to something else, or as electrophiles for something. They won't attract electrophiles. But O and N actually like, or not like, but they can share their lone pairs. So I have 2 different types of reactions that could occur depending on whether they attack carbon or whether the oxygen is going to be involved. So just be aware of that. You don't have it in the haloalkanes because the halogens won't share, but oxygen will share. So as an example here, this is a substitution where I'm focusing on the carbon. So I'm going to have a nucleophile. So this is like SOCl2. The chlorines of the SOCl2 is negative, so it's going to come in and it's going to kick out the OH minus, and I'm going to form also HCl and SO2, because you can see there's a rearrangement of this that happens. So don't worry too much. Just remember that you've got HCl and SO2 forming. So I get that product. Now, I've got the, Joey said, is it more likely to go to C as it is 4 and then N? No. Nitrogen is the most willing to share its electrons. So it's, and then oxygen. Carbon tends to have to have 4 bonds. Carbon doesn't really have lone pairs. So it's either got like a double bond and 2 singles, or 4 singles, or a triple bond and 1 single. So carbon never really has lone pairs to share. But the only time you draw it is in carbon monoxide. So carbon doesn't really come into it in terms of sharing, but oxygen has lone pairs, nitrogen has a lone pair, and also the halogens. But the halogens don't like sharing. They hold on to the, I can't say they hold on to the electrons more strongly, but because obviously oxygen has got a high electronegativity. But it can form, it can rearrange its orbitals more easily than the other ones can. I know that hasn't explained. When you go on, you'll learn about hybridization, and that will hopefully help explain things. Okay, so you've learnt a little bit about hybridization there, Joe. That's for the rest of you, don't worry. If you carry on with chemistry, you'll do more of that. Okay, right, so I can either have it as a nucleophile or I can have the O being involved. And this is an example where the oxygen is acting as the nucleophile. So instead of a nucleophile attacking it, this is a nucleophile to something else. And we'll do this reaction again when we do carboxylic acids, because I hope you realize this is a carboxylic acid. And it attacks the positive carbon of the carbonyl. That OH disappears, and I form an ester. Okay, so this is the way an ester forms, and I have the conch sulfuric acid as my catalyst. Okay, now I know there are multiple attendees typing, so I'll go back to here if there's a question relating to this. Okay, right. And the leaving group is water because it's the OH here plus the hydrogen from the OH. Because you'll notice this oxygen from there doesn't have a hydrogen attached to it. So my leaving group is H2O. So here, as I say, I don't really have time going through the whole thing. I really recommend that you have a look at it. So frankly, chemistry, if you do the tertiary haloalkane preparation, it is like 26 minutes, so we're definitely not going to look at it all the way through. But it does explain the different steps. And sometimes in an exam I've seen saying this is being synthesized, and then in the workup the student does this and this and this and this, and then they'll say, what's the reason for adding this? What's the reason for doing that? So it is important that you have some sort of idea of how to make a substance and the purification. Sorry, I always lose my cursor on these YouTube things. So the purification. So how to get rid of the acid, how to dry my compound at the end by removing the water. That's where I use sodium sulfate. Sodium carbonate is used to remove the acid. And then, as I say, there's this one as well. This one's shorter, and if I just drag it to about a minute or so, okay, then you can see they're first making the HBr in solution. So they're not adding HBr, they're making HBr in solution, so they're keeping it very cold, and then the heating will come later. So if in case you're wondering why is this in an ice bath, when I've said you've got to warm or heat organic reactions, sometimes a particular step, as you can see, I'm using sodium bromide with sulfuric acid to actually make my HBr. So there may be little things like that. You won't be expected to know how to make HBr, so don't think, oh, I can't just learn HBr, I've got to learn how to make it. That's not the case. But it may be that in the exam they will explain this step, and I don't want it to throw you. So by seeing these reactions, you will hopefully sort of know there are all these different ways of doing things. Yes, some sort of awareness. So all you have to learn is, these are your reactants, this is your reaction conditions, and that's your product. Okay, that's your learning work. But as I said, the reactions could come from different ways. They could say they put this into an ice bath, and that's because it's to try and make sure that everything's condensed properly, because it's got a fairly low boiling point. Right, so Niall read and frankly chemistry. I think these are on OTL. If they're not on OTL, let me know, because I sometimes forget to update things and so on. And here's some more. This is now the thionyl chloride, and because remember we had that as a reaction forming a haloalkane. So this is from 1 minute 42. Okay, right. So can you see how it's bubbling away? Because remember what the products were? The products were HCl and SO2. Now, are those gases or are those liquids? HCl or SO2? They're gases. Yeah, SO2 is a gas, and HCl is also a gas if it's not in water. It's just very soluble in water, and it becomes a solution very readily and becomes hydrochloric acid. But in there you can see it's becoming red, so it's acidic because hang on, they're using permanganate there. They're testing the SO2 there. So that's your straightforward redox chemistry, SO2 being reacting. Okay, but they could have also tested it with HCl, that gas coming off with damp litmus, and it'll change the color. Okay, and then this is PCl5, not that important for level 3, but it is a level 2 reaction, so perhaps have a look at it. Okay, now time is ticking by, and you do, this one is, it's about 3 minutes. I'm not actually going to really look at it now because it's not directly important. This is now the esters, because remember we've looked at where carbon is the positive center and we've got a nucleophile attacking it. Formation of an ester is when we've got the oxygen as my reactive center and the oxygen is doing the attacking. So here we're adding the substance, so it's a way we can add a substance to it, and it first gets done, as I say, it sometimes gets done in a cold area and sometimes in a hot area to heat it. It really depends on what stage you're in. This is a separating funnel, and I don't know if you saw those 2 layers. If you listen to it, it explains what they are doing. Okay, I'm not going to go through the whole thing because it's 6 minutes. Do you think you'd be able to find these on YouTube? This one's also Nile Red. Yep. Okay. Have any of you looked at any of the previous reactions I've put on? Or, you know, like the solubility one and so on? Not, okay, it's not yet. Okay, just if you can sometime do that. Right. So with alcohols are actually quite useful, and you'll always find them in reaction schemes because they can be, they've got a much broader range of reactions. So we've seen it where the carbon can act as a, be attacked by a nucleophile and you get substitution, and it can also be eliminated. The haloalkanes had those same sort of things. So the carbon that has the OH plus either from this or from this, that hydrogen can be removed. Now for site Cephs, remember the major product is the carbon with the lowest number of hydrogens. So this one's got 2 and that one's got 3. So the major product will form between the red carbon and the yellow one, and the minor will be between the red and the blue. So conch sulfuric acid and heat, you form the alkene. Now remember also, don't forget your isomers, because can this only form as one product, or could I actually form 2 products over here? 2, because remember this is, you can get cis-trans isomerism, geometric isomerism. This is a trans version I've got here, but you could also get the cis version. So this reaction can actually give 3 types of products: the trans butadiene, the cis butadiene, as well as the but-1-ene. Okay, you can't get cis and trans with but-1-ene, so because the final carbon has got the same group on it, 2 hydrogens. So this would be the major product, and it could be cis or trans. Okay, so the minor product forms between the second, so it's between the red one, because that has the functional group, and then it'll be the yellow one, it'll be the more substituted one. So the yellow one is more substituted because it's got a carbon on it, and it's only got 2 hydrogens. And then, as I say, here's another one where it's a dehydration, and it's a slightly bigger compound. So I think this one is a liquid that comes up, but it's, you know, here you can see he's explaining it, and you can see he's refluxing it. Remember that reflux, the heating, and you know, he explains the whole thing. So I'm not going to go through this. It's just when these get loaded up on YouTube, you can just go through it and check which ones those are and search for it on YouTube. Or it should be in the OTL, so you can just click on them directly. Okay, then alcohols do something that the haloalkanes don't. So that we've got more types of reactions, and that is oxidation. If I have a carbon with an OH on it, and it has a hydrogen on it, it can be oxidized. If it doesn't have a hydrogen on it, it can't be oxidized. So, can primary alcohols be oxidized? So imagine in your mind what a primary alcohol looks like. Yes, you're correct, it can, because a primary alcohol will have the carbon with an OH and at least 2 other hydrogens on it. Okay, perhaps 3 if it's methanol. Can secondary alcohols be oxidized? Yes, this is an example of a secondary alcohol. This red carbon's attached to 2 other carbons, so it's a secondary alcohol, and the red carbon has a hydrogen on it. Can tertiary alcohols be oxidized? No, because there are no hydrogens on it. In tertiary alcohol, this would have been another carbon. So remember what I said, a good way of, only for organic chemistry, of remembering what oxidation is adding oxygen or removing hydrogen. In this case, it's this hydrogen that's being removed. So if you don't have a hydrogen there to remove, it's not going to work. Okay, so if I treat it with permanganate under reflux, it's going to form a, now let's check, do you know this functional group? Ketone, well done. Okay, so it's going to form a ketone. So secondary alcohols form ketones. Okay, if I have here, this is a primary alcohol, so I've got 2 hydrogens attached here, and so either one of those could go, or both could go. So my first step, if I want to stop it at the aldehyde, where I just remove one of them, I have to use slightly less intense conditions. So I use dichromate and not permanganate. I don't know if you remember from your, when you did your 3072 booklet or 3071, those tables at the end, permanganate was a stronger oxidant than dichromate. It was higher up or lowered. Yeah, anyway, it had more positive redox couple, okay, or more positive reduction potential. So this is a slightly weaker oxidant, and if I distill it off, so in other words, the aldehyde has got a lower boiling point than the alcohol, because remember, this doesn't form hydrogen bonds. Water can hydrogen bond with it, so it can dissolve in water, but it can't hydrogen bond within itself to other aldehydes. So it's got a lower boiling point. So what will happen the moment an aldehyde is formed, if you've got it at fairly hot temperature, you'll just simply distill off the product. Okay, and we can stop it and collect the aldehyde. However, if I have permanganate reflux, or if I have dichromate reflux, that other hydrogen will go as well, and so can you see I've lost both hydrogens and I've oxidized it further. So you can see I've added another oxygen. So this is, so the aldehyde is what left. Now the aldehyde, if I wanted to collect the aldehyde as a product, I would just do this step and I wouldn't do this final step. If I wanted to get simply to the carboxylic acid straight away, I don't do this middle step. I just take my alcohol, reflux it with dichromate or reflux it with permanganate, and I get my carboxylic acid. the aldehyde just gets reacted straight away. Okay, and I have it under reflux, so as the aldehyde boils off, which it will, remember the reflux column, it cools down so it can drop back in again, and it'll then react. Okay, so can aldehyde to OH? Yes. No, you don't do aldehyde to the carboxylic acid by distillation. It's always by reflux. Because if the aldehyde distills off, it's not going to react further because you've taken it away, you've removed it from the dichromate. So there's no oxidant there to oxidize it further. Okay, right. And as I say, there's lots of videos here that you can watch. Why these are important is the color changes, or are the color changes. So can you see it sort of looks a bit of a dirty green color? Dichromate, I hope you know, is orange. So what will happen is if you oxidize it with dichromate, the dichromate is going to turn green to the chromium 3 plus ions. So it's also an identification test as well. So if you had an unknown liquid and you wanted to check whether it was an alcohol or a primary or a secondary one, you could react it with dichromate. So there he's showing the orange dichromate. I wouldn't suggest you do it to any old unknown. I would suggest you have an idea that it's an alcohol in the first place. Okay, right. So those, as I say, I suggest you watch so you get an idea of that. So having a look at your alcohol, if I wanted to go from a primary alcohol to an aldehyde, which one of those do I use? 1, 2, 3, 4, or 5, or 6? 5, correct. Okay, the second one over here, ROH2 alkene. So it's an elimination reaction. As I say, start drawing tables. This is an oxidation, this is an elimination. So that'll be number 1, correct. Here it's an esterification. So this is a type of substitution reaction. As such, it's what we call a condensation reaction, but it is a type of substitution reaction. So right, good, 4. And this one, this is a proper substitution reaction. Okay, the SOCl2. As I said, level 2, you learned more, use PCl3 and PCl4. At level 3, it's mainly the SOCl2. And then, yep, this, you can either use the permanganate or the dichromate, if we want to go straight away to the carboxylic acid. And the final one is the ketone. Because the ketone can't be oxidized further, I can use the same method. You know, just bung in some permanganate, acidified permanganate, and reflux it, and I'll get my ketone. Yes. That's why we're doing the organic quite early in the year, so you've got lots of time to get your head around all of this. Okay, 5 minutes for amines. We're not going to get to the aldehydes and ketones. We'll do that next week. Amines, the same thing as the alcohols, apart from the oxidation. But we've got a carbon center there and the nitrogen center as well. You really, at level 3, are going to just focus on the nitrogen. Okay, the nitrogen isn't as electronegative as oxygen, so it doesn't make this carbon that electropositive. So it's not that strongly attracted to nucleophiles like an alcohol is. So at level 3, all you have to learn about is with the amines. So remember, an amine is basic. So in 3.6, you learned about, or you're going to learn about weak bases. And if you've done 2.6, you'd note this. Weak bases accept protons and they partially dissociate or partially form. So what's happened here is it's reacted with a base or it's reacted with water to form the, it's accepted a proton. So this is the conjugate acid of my conjugate base. Okay, so that's the first reaction. It's a base, and it reacts as a base, a weak base. Okay. If you wanted names, the old name is ethyl ammonium ion, and you can call it that, or if you wanted to give it the new IUPAC naming, it's an ethan aminium ion. It's A1M for amine. I don't think that this is ultra important. Yep. So April, I really don't think you have to know how to name it, quite frankly. I've never seen it come up directly that you have to ask, give the name in a reaction scheme. No, I'm just, pointing out the spelling, but you're not going to get marked down if you made it with a double M here. Okay. And you certainly wouldn't be asked for this as a direct, you know how they always give you a list of compounds and say name these compounds, or here are some compounds, draw them. So this will never come up as one of those that you've got to name. It might just come up, as I say, they might describe a reaction and give you all lots of questions about it, and this may come up and they would give it to you. Okay, and then because just like oxygen can go and attack something else, the same thing with the nitrogen, and we saw this already under the haloalkanes. Remember we said haloalkanes react with amines to form secondary amines? So we've come across this reaction before. So here's my primary amine reacting with the haloalkane to give me a secondary amine. Okay, so I'm trying to show what's happening there. The leaving group leaves, and so I form my secondary amine, and it can continue reacting with some more haloalkane, and I can get a tertiary amine. Okay, so, and then the reaction would stop. So this is a reaction you've come across under haloalkanes, and you've come across it in this type of, under amines. Okay, so amines is pretty much just this reaction and it acting as a base. Oh, and then I've got here, as part of the workup, the reaction mixture is treated with bicarb, sodium hydrogen carbonate. Why? Think of what your leaving group is. Okay, it's not to change the gas as such, but the HCl is acidic. Okay, so it's to neutralize the HCl. Yep, so Johnny, to make NaCl, it's just to neutralize the HCl, because you want to have a neutral compound at the end. Okay, and I think, yeah, we can go very quickly. What is the starting material for this? If I want to make an alcohol, so this is another way you can learn, is say, I've got a product, what do I start off with to make that? This will help you with your reaction schemes. You know, if they say, this is the final thing, how did I get there? So I'm forming an alcohol. What sort of thing did I have here? Okay, because that's aqueous. So any secondary haloalkane, that could have been a chlorine. Okay, here I'm using alcoholic NH3 to form this amine. So it's the haloalkane primary, and you've got to have, if it's got 3 carbons in it, of course make sure you've got 3 carbons in it there as well. Here you've added HCl to the middle one. So what could be your starting material? Yep, it's probably the alkene. Joe, OH, I know, and also at level 2 and so on, they say you can add HCl. It doesn't actually work very well. Or it does come up at level 2, you know, to add HCl to an alcohol to form a haloalkane, but it's actually not a very good method. So try and always just use SOCl2. Okay, don't use HCl or those. Only use HCl from an alkene. That's a much better method. And then finally, if I wanted to make a ketone and I'm using permanganate under reflux, what would I have to start off with? Not an aldehyde. An aldehyde would go to carboxylic acid. So great, Caleb, for sorting that. So it would be an alcohol, and more particularly, it would be a secondary alcohol, because a secondary alcohol forms a ketone. Okay, and I think that's it, because now we're going on to aldehydes, and I think we need to leave that for next week. So, Joe, you are doing great, because we're condensing a heck of a lot of stuff. So, as I say, flashcards, I'm going to see how I can make up some Quizlets for you as well. And as I say, making games, putting, what I liked about that sort of organomy type game or that rummy game is you've got to go, well, here's something, it could be a reactant or a product, and you can sort of play around with it. But if you are going to be playing that organomy type game, rather use all the alkenes first and get used to that, and then do all the, say, haloalkanes, and then start trying to mix alkenes with haloalkanes and start building up that way. So, don't try and get lost by trying to do too much. Yep, Phoebe, I don't want you to feel behind, but you will get there. So just, plod on and make lots of things. So when I say make lots of things, I mean flashcards or tables, draw up the different types of reactions, substitution, addition, oxidation, reduction, and so on. And it will get there. Quite frankly, the more work you put in, the more you'll remember. If you're relying just on other people telling you, it doesn't stick in, because you haven't actually processed the information yourself. And that's why typing, you don't actually remember very much, but writing, your brain actually processes information when you write. So I find writing out, for me, what works often if I'm trying to learn new words or new reactions is just writing out the reaction 10 times. And I find then I remember. So, yes. So, Johnny, you can do those 4H reactions for the alkenes. Yep, so pictorial drawing, making images, that will all help. But as I say, start doing it now a little bit at a time, so you'll be totally confident in the exams. But if you try and cram it, that's when, well, for me, I get confused then. Yeah. Yes, and that's why I say that cross-linking with that game helps, or going back, forward. Don't just go forwards, go backwards as well. Okay, we are definitely over time. I know we did lose a bit of time with our wonderful Adobe Connect connections, technology.